Thank you very much, Levi. And we are definitely looking forward for the next couple of weeks where we're going to be doing some experiments. Our next speaker is Professor Christian Cipriani. He's the director of the Bio Institute at the Scuola Superiore Sant'Anna in Italy. And we have had few projects together and a few PhD students coming to my lab. Now he's still in one of mine, and I guess that's the way it is. But please.
Is this working? Hello? Hello. Okay, thank you for inviting me. It's a great pleasure for me to be here, and congratulations for this achievement, and good luck for the upcoming years. So I hope I deserve the honor to be here by giving a decent talk. Okay, so I will talk about a different approach for controlling limb prosthesis, starting from upper limb prosthesis, because that's where we've been working for a while. We call this a myokinetic control approach. The idea is to track implanted magnets. The idea is to track magnets implanted into muscles. Okay, so this was funded in 2015 by the European Research Council. The basic idea is very simple. Anyone who has worked with the EMG sensors know that it's not super easy to actually understand and decode individual finger movements or anything arbitrary movements. One way could be to implant myoelectric sensors, for example, IMEs or other approaches like that. The idea came from that. So at that time, I was in Colorado visiting Richard Weir, and I thought, why don't we put passive IMEs? So why don't we put small things that can travel with the muscle and can give you an information about the muscle? So the idea is rather simple. We don't know if it works. Okay. We put a magnet or multiple magnets in a muscle or in a muscle compartment. Then with all effect sensors, we try to track the movement of those magnets, that is the movement of those muscles. And then we take this information to control the relative degree of freedom in a hand prosthesis. Okay, so if we stick an implant in the flexor digitorum profundus, we would use that information to move the index finger. And you can do the same with different muscles. I think I have a nice video here that shows the idea. Okay, so by the brain you can contract your muscles, then you can put a magnet or more than one. I mean, it doesn't have to be one. If you're able to track the displacement of that muscle contraction, then you can use that information to move the index. Or if you put multiple of those, you could ideally have independent control of multiple degrees of freedom. At least this was the idea. There is also a side part of this project which is about sensory feedback, because there are mechanoreceptors in the muscles, like muscle spindles, which are supposed to convey proprioception information. Okay, especially if they feel vibrations in the muscles. So the idea is to vibrate these muscles through the magnets from the outside in order to provide some sort of proprioceptive information, some sort of proprioceptive sensory feedback. This idea was triggered by the work by Paul Marasco a few years ago in Cleveland. So we started by developing a mock-up and testing if the idea was feasible at all. Okay, we were experts in other part of this story, but not really about magnetic field and localization. Okay, magnetic localization. So there are some models that there are equations that describe the magnetic field generated by a magnet. And if you put multiple magnets, if you have multiple magnets in the space, then you can build a set of equations which describe the overall magnetic field generated in space. If you have enough sensors, if you have enough magnetic all effect sensors, then you can reverse this equation and come up with the place, with the localization, the position of each magnet in space. And when I realized this, I didn't know before, so I thought we would have done a more trivial trivial methods. Instead, we actually realized that this is it's a known problem, so it's called magnetic localization, and it's something possible. Okay, so we first developed a mock-up which had the size of the human forearm with the wires that were resembling the movements of 4 muscles in the forearm. We put magnets there, and basically we tested if this system could work at all. So in these graphs here, you can see the movement of each degree of freedom, so of each muscle, and the relative computed displacement using reversing these equations, okay, from the outside using a number of sensors. While the absolute accuracy is not perfect, meaning that we can have errors up to 1 millimeters out of 10 millimeters of displacement, the precision or the repeatability, which is what we are really interested into. So, which is what how do we? I'm afraid I will switch everything off. Questo? Okay, yeah. No. Too many buttons. Anyhow, the repeatability is good, which means that those curves are straight, okay? Which means that you can learn how to the mapping between the actual displacement and the computed displacement. We were able to demonstrate localization, computation on a median of 45 milliseconds in this first experiment, but I will show you a video because it's much nicer to see. So here what we have a data glove on a healthy hand, a mock-up, a robotic hand, and a HOSPC. So the data glove contains sensors. Okay, it's a cyber glove. Okay, every time you move the data glove, this will move those magnets implanted in the forearm mock-up. Okay, so the data glove moves the wires. The wires carries the magnets. We have sensors outside. Those sensors monitors the magnetic field and localize the position of the finger or of the muscle, which is sent to the robotic hand. This is just for demonstration. We can track 1, 2, 3, 4 movements in parallel. Now the video goes faster at some point, and you can see that this is actually possible. Okay, and as you can see, I mean, the 4 magnets coexist in the same small workspace. I'm talking about magnets the size of a shirt button, and in this case they were virtually implanted in the thumb, flexor digitorum profundus 1, 2, and in the flexor pollicis longus, and in the thumb abductor. Okay, so this would be the 4 targeted muscle that we would try to target, and if we manage to do the first implant. And the system doesn't have to learn anything. Okay, there's no mapping of anything to nothing. This is a reversing equation and mapping the excursion of the magnet to the excursion of the degree of freedom. Okay, of course you can think of putting multiple magnets on a single wire. You can think of putting magnets on antagonist muscles in order to have flexion extension in a more physiologically appropriate manner. So after the first proof that this was actually possible, and we were quite excited, we started investigating more and more about this. How many magnets could we actually track simultaneously? Something that we didn't really know. How many sensors do we need? Which is the best trade-off between sensor sampling frequency and resolution? How can we deal with external disturbances, and so on? Okay, so I will go very quickly into these details by presenting what we did since then. So basically, by simulating, in simulation workspace, we simulated practically an infinite number of with an infinite number of sensors and on different planes. We systematically evaluated the effects of the number of sensors, the distance between the sensors, the distance between the magnets, and the distance between the magnets and the sensor plane. So between the muscles and the outside where the sensors would be. And we found that that angle theta, representative of the arctan between the distance between the magnets and the distance between the magnets plane, a magnet plane and a sensor plane is representative and gives us information about it's descriptive of the ability to recognize different magnets. So in simple words, if this theta is greater than 30 degrees, then the magnetic field produced by different magnets is distinguishable. So you see the different peaks, which means that you can actually see them. Okay. If this theta is instead below 30 degrees, more or less, the peaks are smoothened. So the magnetic field produced by a number of magnets it's undistinguishable. So you only see a great peak, and localization becomes bad. Okay. So here it's written in qualitative manner, of course, but we have a paper demonstrating this. This rule of theta greater than 30 degrees proved to be general across a number of conditions and across magnetization of the magnets, number of sensors, and so on. So this looks to be an important thing, which tells us if I respect this rule, I will be able to localize how many magnets I want. Ideally, infinite number of that. Of course, I would need an infinite long stump. Which wouldn't be the case. So would it work for real? We experimentally assessed this rule and verified it on a physical setup, including real sensors and real magnets and a real localizer. And also, we assessed the same rule on a virtual forearm with the physically appropriate lengths of the muscles, and we learned that if the rule is respected, there is an option to implant at 3 different levels of amputation a fair amount of magnets with the decent localization, okay, with an error below 7% of the excursion. Okay, we always take 10% of error as our limit. Okay, below 10%, let's say we're happy. Greater than that, we're not that happy. How many sensors do we need? So this is a very difficult slide to show because there are too many things on it. But the take-home message is the following. So before we virtually tested the ability to localize, okay, in a theoretical way, using a large number of sensors. We actually found out that we can apply genetic algorithms or even simpler algorithms to reduce the number of sensors that we need. And for example, for those cases we saw before, in a virtually short stump, we can localize 11 magnets using like 20% of the initial number of sensors. So it has to be at least 11 multiplied by 3, but it's a little more than that. So you don't need as many sensors. The more sensors you have in place, the larger time you need to acquire all of them. And when you start having many sensors, that sampling frequency becomes relevant in the computation, in the overall localization time. This is even worse. So we got pretty detailed in what kind of information we would need to have a decent localization, and because we said, okay, we know how many sensors we can put. We can put a subset of those. But what if the resolution is bad, or what if the localization rate is bad, or in the other way around? Should I choose a sensor which is faster, or a sensor which exhibits an higher resolution? Or what happens is if some of them is not perfect, is not ideal? Basically, from this graph that you can see in the published paper, what you can learn is that tracking accuracy is primarily affected by the localization rate. So we care about localization rate, which is directly related to sampling frequency of the sensors. We're not really interested into the sensor resolution. This is especially true because sensor resolution of commercially available sensors is far beyond what we need to have have a decent localization of multiple magnets, remote multiple magnets. Following that, we questioned ourselves how to get rid of mechanical disturbances. One source of error here could be that the socket, meaning the socket where sensors are, can be squeezed towards the skin, and this can get artifacts, movement artifacts, basically in our localization, because the magnets would see, we would see movements that are not there actually. We are working on this, but we found a nice way to deal with this error, which is a compensation algorithm, knowing the trajectories that would be natural, so and would be correct. Okay, so there are ways to deal with this, and recently other investigators at MIT proposed actually to put two magnets, and that's pretty interesting idea to get rid of this error. Okay, because when you have two, you can simply track the distance between them, and that's it, and you don't care if the socket squeezes or not. And we also investigated the effects of normal electromagnetic disturbances that you can normally find in domestic environments, like steel bars, microwave oven, and anything else, how this would affect localization. And we found out that this could be a real faulty situation, and perhaps a magnetic shielding could be envisioned. Although we don't, we're confident that this, shouldn't be the normal situation where you, unless people work in a microwave oven factory, but that's another story. Our first prototype was embedded. Our first prototype was developed in MATLAB. The second one was embedded on a PCB, run on a ARM Cortex based architecture. With this, we managed to achieve computation times down to 5 milliseconds for 5 magnets, which is good enough, I would say. It's rather fast. And here you can see a video. So you have one board with 24 sensors and 5 magnets on chopsticks being moved randomly. And here you can see something. And then the next version we've been working on, it's based on a parallel architecture to cope with the several sensor acquisition, okay, to sample more of them in parallel. The whole idea of a parallel architecture is that. And here you can see another nice video. So here we have 4 magnets on that circle, and these 4 boards are connected in parallel. So ideally this could be placed on a forearm of our first subject. The other, how much do we have? Good. Oh, yeah, so it's enough. It's enough. Okay, so the other part of the study is the sensory feedback. Okay, proprioception is the ability of being aware of the position of movement of the body, so it's knowing where my limbs are, and this is mediated through several receptors in the skin and also in the muscles. And muscle spindles, which are there, are thought to be responsible for conveying proprioception. Okay, especially there is this tendon illusion trick, in which if you vibrate a muscle at 90 Hz, okay, you get the feeling of the elongation of that muscle, or in other words, you get the feeling of the movement of the joint on the other direction. So if I vibrate the biceps with a 90 Hz vibration, you feel that your elbow is extending. Okay, and this works for real. Okay, so this was discovered in the 70s by I can't remember the name, but it's a well-known story. Recently, Paul Marasco investigated this with amputees and after receiving targeted muscle innervation. So we thought that this could have been a nice add to our project. Okay, we don't pretend to actually have electromagnets on a viable portable system, on a real prosthesis to take home, because those would be very heavy, but this could allow us to implement some experiments that were never done so far. In fact, we can use the same magnets that we use for localization also to provide those vibrations using what? Using electromagnets from the outside. So an electromagnet is a coil where we flow current inside. So it's exactly the opposite problem of localization. So it is possible to induce in space magnetic field patterns in specific spots of the space, of the workspace, and keep fixed the magnetic field in other parts. So the idea would be to being able to vibrate specific magnets while keeping fixed the others, okay? And this is important. So, and to do so, you need many more coils, okay? Otherwise, if you try to vibrate one, all the others will randomly move, okay? And this, the outcome would be strange. And so this was, so we call this mice prototype because we made two prototypes. One for working together with Paul in Cleveland, and this is the mice prototype to work with mice, and a bigger one for human testing. Here you can see the ability that we had to learn to manipulate those magnets remotely using electromagnets. So we can have torsion and forces in one direction and in the other direction. So we can have full 6 degrees of freedom control of them. And not only we can implement arbitrary waves like ramps, sinusoids, or square waves. So the idea, and you would see it in the last, okay? So boom, 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 boom. Okay, the idea here is to use these mechanical stimuli to understand if they elicit different sensations in terms of perception by collecting directly from the brain in mice, or see if they make a difference in humans at all, and then which is what we don't know. This is the bigger prototype. Here we showed that the ability of vibrating only one, while the others, this one is kept still. Okay, so and here we have 4. So as you will see, I think this is slowed down. We don't have enough electromagnets here to have full control of the 4 of them, but we can have control of 2 of them. So one is moved, another one is kept fixed. The other 2, the bottom ones, randomly move. I don't know if you can see it. Perhaps it's difficult to see this. And this is our latest version, and we are in these days putting together the tracking and actuation in the same system. When we vibrate through the electromagnets, we induce a super high magnetic field in the space, which tends to saturate our sensors. So we need to cope with this situation, finding strategies for that. But we have students that are doing this, so I'm happy, and I hope they're working right now. We did well. I hope they're not. We also did biocompatibility tests in mechanical resistance, corrosion resistance in vitro and in vivo in rabbits, and we got pretty decent results. We know that we can coat these magnets with Parilene C, and this would last enough and would be fine for our clinical trial. So right now we are preparing the paperwork for doing the first implant in a patient using a prosthesis. And prosthesis, so, and this is where we actually come from, and this has been our research activity for a long time. I'm just showing this hand that Enzo and Jan showed before within the DTOP project. The this is the hand we would use in the Mickey project. Okay, it's a 3.5 degrees of freedom hand with sensors, and it's capable of performing the important grips of daily life as well as gesture. And the important grips are supposed to be lateral grasp, precision grasp, palmar grasp, and neutral position, and then you can point, you can do, no, not this one, but yeah, you can do something. And I think I'm done with this. Yeah, so thank you so much again.
And we have a question. So, will the magnets remain in stable position over time, or is there a risk that they will start to wander around in the tissue? And what is the scale of these magnets? What's the follow-up question here as well?
Okay, so previous studies with IMEs, which have similar sizes, show that the IMEs do not migrate, so they stay there. And this is what we know. The size of the magnets is you can put, so magnets are produced by manufacturers, so you can have it in the size you like and in the shape you like. We're using rather tiny magnets right now, like 2 millimeters diameter per 1 millimeter height. This can be magnetized at the maximum level, which is what we need. They're supposed not to migrate. We will keep them fixed with a magnet outside.
I have maybe one more question. So have you thought about the surgical implantation? Would this be, they're too big to be injectable, I suppose?
Yeah.
So
No, actually not. So they're not too big, but so the important thing is when you implant them, you need to know where the pole. Okay, so you cannot put them randomly, because it's important. It would be important to have the magnetization vector pointing outside to have a better reading. They're small enough to be injectable, but as you teach me, any of those systems which were planned to be injected are not injected in the first trials. So we would simply put it in.
Okay. So if the position matters, will that change when the patient is moving around? No, because it's fixed with the socket.
It's fixed with the socket.
All right. Yeah.
So what would change when you do this? Actually, something changes, which is the geomagnetic field.
Right.
Because that points toward the north. So you need to get rid of that. In fact, we plan to use an external sensor, not sensing the field produced by the magnets, but sensing only the geomagnetic field to remove this from the computation.
To compensate for.
Yeah.
Yeah, we have decades of, or more than that, on the use of EMG, but not on magnetism, not electric field. So it's a bunch of new problems that we haven't really even encountered yet. So.
Exactly. That's
so
why
good luck.
Thank you.
Thank you. Thank you, Christian.
We actually got one more question just from Professor John Sensinger, which probably would be interesting for you to answer. Do you expect proprioception to induce a different sensation with embedded magnet vibration compared to conventional vibration?
So, I'm not sure. I'm not sure we will have enough energy to induce enough vibrations. If so, this could be the same kind of illusion. But honestly, John, this is a difficult question. I have no idea.
Great. Thank you.
Thank you.